Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you understand Newton's third law. So I've written it out here how it's typically written in most physics texts, so we'll go over that. Forces always come in pairs that are equal in magnitude and opposite in direction. A lot of times mathematically you'll see it kind of written like this. Any sort of force we'll call 1, 2. There's another force which is equal to it that we're going to call force 2, 1, and they are in opposite directions. So I think the best way to learn it is to look at different systems and the different types of free bodies that you can draw for the different systems. So I'm going to go ahead and do that. Oops, there we go. All right. So we got three different systems we're going to talk about, and we're going to talk about these systems in context of force vectors and free body diagrams. So the first case here, let's talk about this car right here. Right there. And imagine that the driver of the car gives it some gas. All right, now when we draw a free body of the car's got a weight vector down. I usually label those mg. All right, surfaces in contact at the tires, that's going to give you 4 normal forces. It's pretty common to just lump those together into one force up. We'll call that the normal force. And then the frictional force acting on the car acts at this point right here, if it's a front-wheel drive car, and that frictional force acts in this direction. Now, hopefully, if you've seen my videos on how to draw free bodies, or anybody else's for that matter, remember that force vectors have what's called a line of action, and you can draw this force vector anywhere along this line. Now, if we ignore air drag and other small effects, that's pretty well it. Now, let's kind of talk about Newton's third law and how it applies to the car. Every single one of those forces has an opposite force somewhere acting on something else, taking them one at a time. This upward normal on the car, acts down on the ground at these contact points at the tires here and here. Right? Just imagine a bug under the tires there; it would get squashed due to that normal force. This frictional force, which is right on the car, acts left on the ground. I think the easiest way to see that is, imagine if the person really stomps on it. The dirt would fly to the left, again, kind of demonstrating that force is to the left on the ground, right? And then the gravitational force, and this one is probably the toughest for most people to visualize here, but that is the force of interaction between the car and the Earth, the entire planet. So that force is down on the car. Well, that force acts up on the entire Earth. All right, well, moving along. Let's talk about this rocket ship. So imagine that the rocket engine is on. All right, and what that's doing is it's combusting fuel, and it's pushing the fuel out the back. So if we were to draw a free body of the rocket, again, if it's in outer space here, right, there's going to be a force that we would call thrust or something like that. I'll just call it F for thrust, that on the rocket would be to the right. Now again, remember that force vectors have what's called a line of action. We can put this force vector really anywhere along this line, right? But here's a good place to leave it for now. Now, you notice I kind of separated off the rocket from the fuel. So again, within the engine of the rocket, the force on the fuel is to the left. Now this picture bothers me a little bit. I thought about not using this as an example because it makes it kind of look like when the fuel is outside of the rocket, there's a force to the left, and that's not true. Right? So this picture right here, you have to realize this force is acting on that fuel in the context where the fuel is actually internal to the rocket. Right? So these forces, both of them occur when the combustion is taking place within the rocket engine itself. But I'll go ahead and leave this out here. All right. Another example here. We got this system right here. And we imagine we're coaxing the T-Rex to come after this sheep here to get him to pull this big truck. All right, and let's talk about forces acting on the T-Rex. So the picture over on the right, let's see, I'm going to cut the rope for a moment. And we're going to draw free bodies of the T-Rex and the truck. So the force vector, right, due to the tension in this rope, right, that points left on the Rex. So I might put that something like this. And it's a tension, so I'm going to call it T. And then the gravitational force for the Rex is down, mg. Now, surface and contact right here, so that's going to create an upward normal force, upward on the Rex. And the Rex's feet are digging in, that's in creating some sort of horizontal force. I'm gonna put F like it's a frictional force, but I want to point out that may not be a purely frictional force. If the Rex's feet is kind of digging into the ground, it may be like horizontal normal forces. The nature of this force is not super important for the discussion. It's good enough to suffice to say that there has to be a force to the right, allowing the Rex to pull the truck. You know, just imagine if the Rex was standing on a frozen lake, he probably couldn't pull that truck along. There's some sort of force interaction, horizontal force interaction between the Rex and the ground. All right. Now let's talk about the truck now. All right. So this force vector, this tension, which is to the right on, to the left on the T-Rex, that same force vector acts to the right on the truck. And it would be equal magnitude, same direction. That's Newton's third law. There's a gravitational force down. Now, I'm not really paying attention to relative magnitudes, not important for this discussion. The tires are, the ground is supporting the truck, right? That's creating an upward force that we would call a normal force. And it's a different normal from the one with the, on the T-Rex. So I'll put an N sub T here for the normal on the truck. You notice I put a different M here to distinguish that it's not the same as the mass of the Rex. Not important for the discussion. So let me go through all these force vectors and talk about their opposite pair. All right, so the tension here, left on the Rex, by Newton's third law, there's a tension right on the truck, equal magnitude. This horizontal force on the Rex, its opposite pair would be left on the ground. And again, imagine, you know, the Rex kind of spins out a little bit. It would throw dirt or something to the left. This normal force, which is up on the Rex, right, its opposite pair would be down on the ground. And again, equal magnitude. This mg vector, that's for the weight of the Rex. It's down on the Rex. Its opposite pair would be up on the entire Earth. This normal, right, is up on the truck. Its opposite pair would be that same normal acts down on the Earth. And then this gravitational force vector. That's the force interaction between the truck and the Earth. That's what we call weight. And it's down on the truck, and its opposite pair is up on the Earth. So I hope that this video helps you understand Newton's third law. Again, forces always come in pairs, equal in magnitude, opposite direction. So for every force vector you draw on a free body, you should be able to identify an opposite force acting on some other object. So anyway, I hope that this video helps you understand Newton's third law. Have a great day.